Wiley homework?
It's written homework 4.4, number 11.
Okay, so let's look at 4.4, number 11. So I'm looking for the absolute maximum or minimum value on this closed interval. So really, I need to find my critical points on this closed interval. Once I've done that, I test them and find the maximum and minimum. So the issue seems to be with finding critical points. Is that correct?
Yes.
Is the problem? Okay, so 4.4, number 11. So we're given a function. So
I just when I took the derivative of it, that I just felt like it wasn't anything I could do anything with.
So it's the algebra, really.
Yeah.
So plus 1, and we're looking for minus 1 to 1. So taking the derivative of a quotient, I take the derivative of the top, which is 3, hold the bottom, minus the derivative of the bottom. What did I forget? The 8x, right? That's a very common thing to forget. Hold the top all over 4x squared plus 1, the square root of that squared, right? So I do kind of have a mess here. Not going to deny that. But it should be something relatively easy to simple. The denominator never equals 0. So that's one thing that's nice. So here I want to set, when does this equal 0? Well, this is only the third time today I've taught Calc 1, so bear with me. The denominator never equals 0, so I can focus on the numerator. So cleaning this up a little bit, I have 3 the square root of x, or 4x squared plus 1 minus the quantity, what would this be, 24x squared on top. And on bottom I have a 2 the square root of 4x squared plus 1. When does that equal 0? Find a common denominator and simplify. So if I do that, I end up with 3 times the quantity 4x squared plus 1 minus 12x squared equals 0. If I multiply top and bottom by the square root of 4x squared plus 1, the square root goes away and the square root goes away down here. All over that, right? So then this would be all over, again, the square root of 4x squared plus 1. But that doesn't matter because that doesn't equal 0 either, right? So I need to just focus on when the numerator equals 0. So then I would have 12x squared plus 3 minus 12x squared. Does that ever equal 0? So it never equals 0, right? It's always positive. It's concave up. So that tells me my endpoints are my only points to test, right? So if I test the value of the function at minus 1 and the value of the function at 1, at minus 1, minus 3 over the square root of 5. And at 1, I have 3 over the square root of 5. So the maximum's 3 over square root of 5. The minimum is minus 3 over square root of 5. So there's no critical points in the interval. The derivative never equals 0.
So because 3 never equals 0, that's why you...
Correct. There's no value of x that satisfies this equal to 0. More specifically, there's no value of x in the interval. So if we would have gotten this equals 0 when x is 5, the answer would be the same. What was the question? Find the absolute maximum and minimum values of the function on the given closed interval and state where those values occur. So the maximum, so we would have the maximum is 3 over square root of 5, and that occurs at x equals 1, and the minimum is minus 3 over square root of 5, and that occurs at x equals minus 1. So if we verify that, that's what they want. So it turned out here the derivative didn't give us any information. It didn't give us anything more. Our only points we have to test is that interval. It would be very similar to the example of if I said, you know, y equals x.
Yeah.
The derivative is never 0, right? From minus 1 to 1, the minimum point's here and the maximum point's here. You don't have any critical points to potentially be. The global maximum, the global minimum will be critical points or endpoints. In this case, there's no critical points, so it has to be endpoints. So, does anyone have any questions on the algebra? A lot of times when you have, you know, something to the minus 1/2, write it as a fraction and then find a common denominator and simplify. You could multiply through by x, the whole thing by 4x squared plus 1 to the 1/2 power, and that's going to cancel this to be 1 because it would be to the 0 power. So there is other ways you can look at it, but question?
So the algebra, how did you get from the second step of the derivative to the third?
Here?
No, yeah, from there to there.
So
No. The second step, that one.
this one from here to here, or from here to here?
Okay.
Right there.
Here
The next
to
one.
here.
Yeah.
So I multiplied this expression by the square root of 4x squared plus 1.
Denominator.
So I got a common denominator. My common denominator was this.
All right.
So this expression doesn't need anything on top because it's already
Yeah.
the square root of x. Or I could multiply the whole expression by the square root of 4x squared plus 1, and it would cancel here, and then 0 times that, since it's never 0. Right? I could have just easily have written this whole thing, right? And that's going to cancel here, and then this times this is going to get rid of the square root. And then 0 times that is 0. Then I wouldn't really have to worry about the denominator. It's still there, but it cancels. Any other questions on the written homework?
Number 16, 4.4.
4.4, number 16. So along the same lines here, we have to be a little bit careful here because it said, for the extreme value theorem on a closed interval, our hypothesis was our function was continuous. And was it continuous? So we don't have a problem here. This function is continuous. I don't have any non-continuities here. It's not differentiable everywhere because it has that corner, but it's continuous. So I have to look at potential critical points. So what do I have here? Number 16. I have my function f of x equals 6 minus 4x, and that's from minus 3 to 3, and I want to find the maximum and the minimum. So finding the critical points, well, first off, I want to set when the derivative equals 0 or it's undefined, right? So I can break this up into two parts. What would this be? When does 6 minus 4x equal 0? Well, 4x equals 6, so when x equals 6 over 4, which would be 3 over 2. So 3 over 2 is definitely in this interval. So when x is less than 3 over 2, this would be minus the function, right? To get rid of the absolute value, I would take minus the function. And when x is greater than 3 over 2, I would take just the function. If I was to graph this, this is a line, right? It has an x-intercept at 6, and it has a slope of minus 4. But the absolute value would then invert the line, right? So if I was to graph just 6 minus 4x, I would have I would have that, right? This would be the line. This would be x at 2/3. Sorry, 3 over 2. So the absolute value of that is going to look like this. So if I plug in minus 3, what would I get? 12 plus 6, so 18. So this is minus 3 comma 18. And if I plug in 3, I get minus 12. So I would get a positive 6. If I plug in 3, I would have 6 minus 12, which would be minus 6. So it would be a positive 6. So this would be 3 comma 6. Few different ways to look at this here. The slope is constant, a 4, right? The slope on this side would be a positive 4, and the slope on this side would be, sorry, switch them. A negative 4, and the slope on this side would be positive 4. Because the slope of this line is 4. And the absolute value of that is 4. But the absolute value of a function, to get rid of the absolute value, if that function is negative, which if I plug in a number less than 3 over 2, if I plug in 0, it's 6. Positive 6.
So it's reversed.
I switched them, didn't I? If I plug in a number greater than 3 over 2, it's negative. So yeah, I need to switch these here, sorry. This would be if x is greater than 3 over 2. And this is if x is less than 3 over 2. Wait, if I plug in 0, 0 is less than, I get the original function. Okay, I got it right now. We will look at more of this in chapter 5 with this absolute value. This absolute value function, if I take the line, if I take the absolute value of it, it's above the x-axis, I leave it alone. If it's below it, I just reflect it about the x-axis, right? So I get this v. You could also say this is an absolute value function that has a horizontal stretch at 4, and it's shifted over 3 over 2 units to the right because of 4. So now I need to test any critical points. The critical points would be 3 over 2, and then you test f of 3 over 2, and f of 3. So f of minus 3, f of 3 over 2, and f of 3. This would be 18, 0, and 6. So the maximum is when x is minus 3. The minimum is when x is 0. X is 3 over 2, which is 0. Question?
Why didn't we take the derivative and say?
Well, the derivative is 4. It's constant, right?
Okay.
So the derivative exists everywhere. This function is continuous everywhere, but not differentiable everywhere. It's not differentiable when the derivative is undefined. The derivative is undefined at corners, right? It's kind of like that absolute value function. So the absolute value function is a piecewise defined function. If the function is negative, I can replace it with negative the function, right? If an absolute value of a function is evaluated to be negative, I can get rid of the negative by multiplying by negative. Right? So really this is minus the function. The derivative of minus the function is still going to be, it's just going to be 4. And the derivative of just the function, sorry, this in case would be minus 4. In this case would be minus 4. So the derivative doesn't get me anywhere. So I have to look at more information. When's the function not continuous? Well, the derivative doesn't equal each other at 3 over 2. Because on one side it's negative, on the other side it's positive. That happens when the function equals 0. When the function equals 0.
So if it was like a more complicated function inside the absolute value, then we would take the derivative, but since it's kind of basic.
If it was a more complicated function, you would still have to kind of split this up into 2 cases. When's it positive, when's it negative? And that would be your point of discontinuity. This function's not differentiable at this point. So then I can't talk about the derivative at that point.
Because it's that.
Yeah, and so that's just a corner, and this is going to be a critical point, but not a stationary point. It exists, the value of it's 0, but the derivative doesn't exist at that point. The derivative doesn't exist because the way we break up an absolute value. So it turns out you're going to deal with this later on in chapter 5, and absolute values will always deal with a special way.
So they're kind of like that one exception where you kind of have to go about solving the difference.
Kind of, yeah, you do. You can apply the easier technique to it, but it's a lot harder to do because the absolute value you have to split up into 2 functions, and you have to find the interval in which the absolute value when it crosses the x-axis. So if you have a more complicated function, so if I have a function, let's say, that looks like this, and I want to take the absolute value of it, I have to break it up on this interval. Here it's just the function, but in this interval it's minus the function,
Okay.
and in this interval it's the function, because the absolute value of minus a negative would bring that to the top. So when it's a line, it's pretty straightforward. So if I have something like this, then the absolute value will go like that, because linear has the same slope.
That's where-
So you want to find this point and test the endpoints, and those are the only thing you need to know about it. Eventually, we'll talk about the area underneath the curve in chapter 5. And so on an absolute value function, you can use geometry to find the area of this triangle plus the area of this triangle. But if you try to use the fundamental theorem of calculus to learn, it won't come out right unless you break up your intervals in which your function is on.
Can you clarify for me real quick what it is, the first derivative test and the second derivative test? Is the first derivative test just
Maximum, minimum points.
finding your where it's increasing and decreasing
Correct.
on your line?
Yes. The first derivative test can tell you when your function is increasing and decreasing. More so, it can tell you possible local maximums and local minimums.
Okay.
And then on top, so here we have to test the endpoints as well. This is a local minimum. It turns out to also be a global minimum. But yeah, the first derivative test, if I draw that, and let's say this is A and this is B.
I
And
think
if
I'm
I
doing
have-
these things, I just don't know what they're called. You know?
Yeah. This is the first derivative test, and it tells you when your function is increasing and decreasing.
And then the second derivative
It
test?
tells you when your function is concave up and concave down.
Okay, so is that the same thing as whenever? Okay, so we have an open and closed interval. So
Don't
if it-
worry about the open and closed interval. On Wiley, they wanted you to put in closed intervals or open intervals. But if say the function's increasing on minus infinity to A, and you put that, it's perfectly fine. If you put this, you're still going to get the right answer.
Okay, well, what about testing points? Like with open and closed intervals on word problems, when you find your own intervals?
Yeah.
How do you know, I guess, what points you're supposed to test? Because I'm getting the right answers, but I don't know how I'm supposed to tell specifically whether it's the max or the min or.
Okay, a lot of times in word problems you'll get 1 point.
Yeah, that's what I'm.
So then you can do the second derivative test to test to see if the second derivative is concave up, that critical point is a minimum,
Yeah.
right?
Okay.
If the second derivative is concave down, that critical point is a maximum.
Yeah. Okay.
So a lot of times the second derivative test will be powerful in that case. The first derivative test, if you have positive minus, that is a local maximum. And it turns out if you have one critical point on an open interval,
Local equals global.
yes, if it's one, if there's only one. And it's a local maximum, therefore it's a global maximum.
So the intervals really, I guess, aren't that important. Like when
In
the word problems.
applications, yeah, because you don't want to come out like the radius of the can problem.
Yeah.
You might get something that's like 3 or 5, but 5 might not make sense for the volume. So 3 is the only one that makes sense in a specific interval.
Okay.
There's a problem in your book that has to do with shipping a package, and it's like XXH, and the height has to be longer than the width.
Yeah.
So here that you have to pick the one where the H is greater than X. So there might be 2 there, and that keeping that in mind in your interval will give you the right one there, right? Because if you think about a box, if it's XXH, if I flip it over, it's XHX, right? But shipping it shouldn't matter. So they're wanting you to, the square base versus that the base being XH and the height being X, which would be a different box, right? The dimensions would be different. So they want you to have XXH. So your box is square and your height is H. Questions? 4.1, number 29. 4.1, number 29. This LN one. So we're looking on increasing, decreasing, concave up, concave down, and inflection points. So this one should be pretty straightforward. You find the derivative, you set that equal to 0, and you look on when the increasing and decreasing. You find the second derivative, you set that equal to 0, and you look for concave up and concave down. When your interval switches concavity, that's an inflection point. So 4.1, number 29. So I have the function equals ln of x squared plus 1. And I'm looking for, was it 4?
Plus 4.
Plus 4?
It's a square root.
That, nothing else? Okay. So I take the derivative of this function, 1 over the square root of x squared plus 4. So the derivative of the outside, evaluated the inside times the derivative of the inside, times the derivative of the inside. Luckily, it simplifies quite nicely. It simplifies to x over x squared plus 4. Because this is x squared plus 4 to the minus 1/2, so it's really in the denominator. The square root of x squared plus 4 times the square root of x squared plus 4 is x squared plus 4. So when does this equal 0? When x equals 0, right? The denominator never equals 0, so I don't have to worry about critical points being undefined. I only have to worry about stationary points. So if I plug in a negative number, the bottom's always positive, so then I have negative, positive. So the function is decreasing from minus infinity to 0 and increasing from 0 to infinity. So then I take the second derivative. Don't try to take the second derivative from here. Look at your simplified expression, right? So then I do the quotient rule, the derivative of the top, hold the bottom, minus the derivative of the bottom, hold the top over the bottom squared. When does that equal 0? Well, we have minus x squared plus 4 equals 0 over x squared plus 4 squared, which would give me x to be plus or minus 2. So always try to label your graphs. So if they're asking you about particles speeding up or slowing down or whatever's going to potentially be asked, you know exactly what this is telling you. This is increasing, decreasing. This is concave up, concave down. So that's helpful to see. For me, grading it, I can say, okay, you understand this part. But when you don't label it, I don't know which one is which. So be careful with that. So let's say I plug in a negative large number. A negative number squared is positive, but I have a negative out in front of that. Plus 4, this whole thing would be negative, and the bottom's always positive, so I actually have negative, positive, negative. So I'm concave down on this interval, concave up on this interval. My inflection points are plus or minus 2. Make sense? Any other questions? Nope. So, Wiley, just real quick. The assignment due tonight cover up to 4.6, which would be everything covered on the exam. That's Thursday. 4.8 we're going to talk about today, and I'm not going to have that due until April 22nd. So this week focus on studying for the test, and then you take the test on Thursday, and then that next Monday nothing's due. So I know this gets a crazy time in the semester with everyone trying to wrap up everything, and since we have snow days on top of that, trying to get to where they need to go in each of your individual classes, this will just give you a little bit of a breather. Study for the exam, focus on that, and then take the weekend to kind of recuperate, and then be ready to come back that next week. So, today we're going to cover 4.8. 4.8 covers two different theorems, Rolle's theorem and the mean value theorem. Rolle's theorem is a special case of the mean value theorem, so really it covers one theorem. Rolle's theorem is specifically when the slope of the secant line is 0, and mean value theorem is more general. So let's look at graphically an example of Rolle's theorem. I really think pictures help in this section. If I have a function, say I just have a function like this, and this is point A, and this is point B. What Rolle's theorem states that there has to be a point C in the interval which the slope of the tangent line equals the slope of the secant line. More so the slope of the secant line is 0, right? So 4.8.1 is Rolle's theorem, and it states that if you have a continuous differentiable function on a closed interval AB. So those are our hypothesis, that it's continuous and differentiable on a closed interval. If those conditions are met, if the function at A and the function at B equals 0, then there is at least one point, we'll name it C, in AB such that f prime at C equals 0. Right?
That plus is A and B.
Yes. So this is and. Sorry about that. Get rid of that. So if A and B equals 0, so that's being the slope of the secant line being 0. And there has to be some point C here that the derivative also equals 0.
Is that on point or 1 point?
1 point, at least 1 point. Yeah, on point. Just drop my E there. Thank you. At least 1 point. There can be more. So an example of them, a graphically example of them being more. See if I have something like a function that looks like this. If this is my point A and this is my point B, it turns out it equals 0 here, it equals 0 here, and it equals 0 here. So it kind of turns out there's 3 C's in this interval that satisfies this relationship. But there has to at least be one. Right? So just kind of make a note here. Rolle's theorem is a special case of the mean value theorem. A lot of times in math they do that. For special cases they give it a different name. Someone else discovered it or whatever. The mean value theorem is a more generalized theorem, or more generalized the writing there.
Did that one come out before the Rolle's theorem?
I don't know too much about the history and who Rolle was to come up with it. It happens a lot in math. Like in Calc 2, you'll talk about Maclaurin and Taylor polynomials. Maclaurin Maclaurin polynomials are specifically about the point x equals 0. But Taylor polynomials are any point. So in this special case, when you're looking about it at 0, it's a Maclaurin polynomial. But when you're looking at it x equals 1, it's a Taylor polynomial. So it's like someone comes up around the point x equals 5, we call it the Van Ryan polynomial. Whatever, it doesn't really matter. So it's kind of funny that you see that quite a bit. So yeah, you can name your own theorem. But let's look at the mean value theorem. I mean, there's a lot of applications to Rolle's theorem when you specifically talk about, if you had an average velocity being 0, meaning you had to have velocity being 0 at some point in time. So sometimes 0 is useful to use. But the mean value theorem, so if I kind of graph an example of what we have here, let's say we have this point as A. Let's call it A comma f of A. And this point here, we'll call it B, being B comma f of B. So I have a slope of a secant line between them. In this case, I draw it not to be 0. So what the theorem states that if the function is continuous and differentiable, so along the same thing, so f of x has to be continuous and differentiable on AB, then there is at least one point, we'll call that point C, in the interval AB such that the derivative of the function is going to be equal to the slope of the secant line. Secant E-C-E-N-T line. Right, so we're used to taking the derivative and setting it equal to 0 because we've done that multiple times. Those are critical points. That's Rolle's theorem. But it might be the case that I want to find when the particle is going 5 miles an hour. If it went an average of 5 miles an hour, then it has to be going at least 5 miles an hour at some point in this interval. So here, drawing it, it might be this point here. We'll say this is point A, this is point C, this is point B. At C, this slope would be parallel to the slope of the secant line. So that's when the derivative at C is going to be the same as the slope of the secant line between A and B. So let's look at some applications of this. And then we'll look at an application where the hypothesis isn't met, so therefore the conclusion isn't necessarily. And that actually involves absolute value. So in the case we're going to ask to confirm that f prime of C equals 0 between the two x-intercepts, right? Because the x-intercepts would give me a slope of 0 for this function. So what are the x-intercepts? Yeah, so if I factor out this, I have x minus 4, x minus 1 equals 0. So at x equals 1 and 4 would give me the x-intercepts. So on this interval, the derivative equals 0 at some point in this interval, the derivative of the original function. Your book calls it C. So if I take the derivative of the function evaluated at C, that's going to be 2c minus 5. Set that equal to 0 and solve for C. C would be 5 over 2, which would be 2.5. Oh, sorry. 2.5 is in this interval, so we've confirmed it. The derivative of the function equals 0 at 2.5, which is in between the x-intercepts of 1 and 4. So if I was to graph this, this is a quadratic that opens up, that has an intercept here, and here, and so it looks like this. Potentially. It's always, there we go. So this point being C, that's the point you're solving for. So this being said, your book uses this notation, the C. If you want to use X, that's perfectly fine. And then just know that that C they're looking for, if you want to say X is 5/2, so that's the value of C in the interval. But your book tries to get away from using X and saying, okay, we're going to plug it in at some C value. So if I take the derivative and plug in it at C, this C has to be within this interval. Some of you look a little like you don't like that. Is it seeing the derivative in terms of C instead of X?
So it's just a relative extreme. Is that?
Here, it's saying that this is the point in which the derivative equals 0. The derivative is the same as the derivative between the two x-intercepts, right? Let's look at an example where the derivative is not 0 and how to go about that. So let's look into the example in the graph. Parallel, mean value 0. Okay, so let's say we have the function f of x equals 1/4 x cubed plus 1 on 0 to 2. So here we're going to find all values of C on 0 to 2, which the tangent line to the graph of f of x is parallel to the secant line joining the points 0, f of 0 and 2, f of 2. Right, those would be my 2 points. So I want to find the all values C on this interval for which the slope, so the derivative, is going to be the same as the slope of the secant line. First thing I need to do is find the slope of the secant line. Once I do that, I take the derivative and set it equal to the slope of the secant line and solve for the values of C that satisfy that. Make sure that they're in this interval, though. They have to be. At least one of them has to be in the interval. Do you see how that's a little different than what we did here? Right, because here the slope of the secant line was 0. So I take the derivative and set it equal to 0. So what is the slope of the secant line? So the slope of secant line well, that's f of 2 minus f of 0 over 2 minus 0. So f of 2 would be 3. F of 0 would be 1 over 2, which would then be 2 over 2, which would be 1. Right? So now I want to solve for when the derivative equals 1. Right? So what is the derivative at C? Well, the derivative would be 3 over 4c squared equals 1. Okay. I'm just replacing x with c. So I know that that c is in between a and b. So here, when does c squared equals 4 over 3? When c is 2 over the square root of 3. Plus and minus, right? But it turns out I'm looking on the interval 0 to 2, so here c would be 2 over square root of 3. So when c is 2 over square root of 3, then the derivative has a slope of 1. Does that make sense? So a lot of times they'll say, you know, you've done examples like this before where they say ask where the slope is parallel to y equals x. So you take the derivative, you set that equal to 1 and solve. It's along the same lines. It's just worded a little differently. They just give you this interval from 0 to 2, and you're finding when the slope is the same as the slope of that secant line. So in this case, the slope of the secant line is 1. So you take the derivative, set it equal to 1, and solve for the value of c that makes that true.
Is that usually going to be, well, I guess slopes are known as nice numbers.
It could be anything. It could be.
Yeah.
It could be 3 over 4.
Yeah.
So then it could be anything. Yeah. Square root of anything crazy. So the consequences of the theorem, of the mean value theorem, are along the lines of the consequences of what you already know. If I have to get from, or if I know the function is increasing, right? The secant line is positive, then the function has to be increasing on that interval, right? If I know it's increasing, the secant line has to be positive. If it's always increasing, the secant line has to be positive. If it's always decreasing, the secant line has to be negative. Some things that we've talked about before, right? That if the derivative is positive, my function's increasing, right? So if my slope is always positive, then the slope of the secant line has to be positive. My function's always decreasing, then the slope of the secant line has to be negative, which ties into the derivatives, right? So the last thing we're going to have time to probably talk about is the constant difference theorem. Which will come up in Chapter 5 and in Calc 2. So let's say we have f of x and g of x. We're assuming they're differentiable on a closed or an open interval a, b. And if f prime of x equals g prime of x for all x in AB, then f minus g is a constant. So this is saying f of x minus g of x has to equal some k, or you could say f of x can be written as g of x plus k. The constant difference theorem here is going to come up again in Chapter 5 when we talk about going from the derivative to the original function, right? So let's look at an example here. Let's say x squared plus 2. Right? If I take the derivative of this function, I get 2x, right? If I take the derivative of g of x, I get 2x. Right? Because the derivative of a constant is 0. So if I know the derivative function and I want the original function, in this case, if I have the derivative is 2x, the original function is x squared plus any constant, right? This is where this constant difference theorem comes into play. Eventually, we're going to talk about the antiderivative. So if I give you a function, I want you to tell me, if I give you a function that is a derivative, I want you to tell me the original function. And that's called antidifferentiation, which is also called integration. So if I have a function and I differentiate it, you can do that, right? I give you a function, you can differentiate that. Chapter 5, I'm going to give you a function that has been differentiated and ask you for the original function. And that plus c is very important in here. So it turns out, in this case, that the original function is always in the form f of x or g of x is in the form x squared plus some constant k or c. Right. This is also used in differential equations a lot of the time when we talk about a family of solutions. So if I think of, this is a differential equation. If I take the function and I differentiate it, I get e to the x. Does anyone know any function that I differentiated? I get e to the x? E to the x. And it's actually e to the x plus c, right? E to the x plus c. So if I was to graph, I have a family of solutions here because c can be anything. So eventually, if I say the solution to a relationship like this, differential equations in lower level math, you talked about finding a value to satisfy an equation. And then in college algebra, you talk about a function to satisfy a relationship. A differential equations, you talk about a function to satisfy a relationship. So you're not looking for values, you're looking for functions. In this case, is the family of solutions. So this C also plays a role from the constant difference theorem. Question?
So the f minus g,
Mm-hmm.
that would be like what the x squares would cancel, and then you're just dealing with
The constants,
and
yeah.
That's where
So what this is saying that if the derivatives equal each other, then when you subtract the two functions, it has to be a constant. This is used in your book to prove a trig formula. So this is 4.8. Your book uses this, and we don't really have the time to go through this, but I don't know if you know this identity from trig. So it turns out if I take the derivative of sine inverse plus the derivative of cosine inverse, I get 0. So it turns out that if I differentiate this function, it's only off by a constant pi over 2. So the derivatives are equal to each other. So the derivatives are equal to each other. So that you can use this theorem to prove this identity. So they can only at most be off by a constant. Then if you take this function and differentiate it and take this function and differentiate it, then they're equal to each other. So they can only at most be off by this constant. It turns out they're off by pi over 2. So you can use it to prove theorems in some instances, and that's what your book uses it for. We will use it later on in chapter 5 when we talk about integration, and that you see these plus c's, they come up all the time. So if I integrate something like this, I get this, because if I differentiate this, I get this. That's what we'll end up doing. So you need this plus c, it's very important. And then we might solve for initial condition that when I plug in x equals 0, I have to have 5. So then this specific case would be x cubed over 3 plus 5.
Where you're only given one part of the equation, you gotta solve for.
Yes. Yeah. So eventually we're going to get there. All right. I will see you guys tomorrow. Homework is due in my office by 5 o'clock. And then I will email you guys out a review sheet.